Hi folks, I've just split up a production of a single video into two parts, and I'm going to pick up here where I show how to calculate this expression here. Okay, the expectation of x over a certain threshold, which is related to the Pareto type 2 distribution. Now, this is the expression that we're specifically asked to evaluate and get a value for. Now, the average net claim is given by that expression there. Now, that requires a bit of actuarial knowledge that's beyond mathematics to know what the definition that you're asked for and net of the deductible, and that it actually should be expressed as follows. But here, if you're not familiar with this actuarial stuff, that is what we're asked to do. So it's broken up into two parts. Okay. Here the threshold is denominated as D. Okay, so just switching the expression above, we are going to just call it D as opposed to T, the threshold. We also have to find this as well. This is not particularly hard. I'll come back to that later on. Okay, I'm going to just use that expression from the tables to calculate that part. This is the one that requires a good bit of work though. Okay, now the evaluation here, sorry, I have the wrong limits there. So it is the limit from D to infinity, okay, so it's over this threshold of x minus d given this probability density function, okay. So it's a definite integral of x minus d times f of x dx, okay. Now first off, what I'm going to do here is demonstrate that we can break this up into two parts. So we have x minus d times f of x, so we can break this up into one expression here, okay, and another expression here, okay, so it's broken up into two. Now this second expression here, well, what's this? This is actually the probability of x greater than d, okay, this one, this part here, okay, that there. So essentially what we have here is this expression here. Let me just be clear about that. This expression here can be written as follows. D times the probability of x greater than or equal to d, greater than d. Okay? So that's not too bad. You should spot that fairly quickly. So what we're asked for here is this expression here. Okay? What we have to do is calculate that. And we're evaluating it from d to infinity. Remember that. It's not simply the mean. It's not the expected value of x. It's those. It doesn't have those those limits of integration. Okay. Now what we're going to do is show that it actually evaluates as follows. So I actually have the answer here. Okay. So I want to signpost a couple of things as I go. This expression here only, you can disregard this, evaluates this term plus this term, okay, and what that means is this term and this term, which are opposite signs, cancel out, okay, so that's why you end up with this expression here, okay. So you have to just actually have a very clear idea of how this process continues and how things cancel out, okay. So this expression, so that's important, that you should get an expression here and this expression here, and they ultimately cancel each other out. So this is the main expression that this is your end result essentially. Okay, so here it's expressed in terms of t, but let's go switch it back to d there for a second. Okay, this is the key calculation. This is why I'm spending a lot of time with this in this video. Okay. Because you really have to know this and be able to cover this at some stage. So what we're going to do here is use integration by parts to solve this. Okay. Now, the u term is actually all of the numerator. Okay. So it's x times alpha times lambda to the power of alpha. Okay. That's the u term, and the dv term is this expression here, okay, and where do I have that? So dv is down here, sorry, yeah, this expression here. Okay, that should be with respect to dx actually. Okay, so when we differentiate u to get du, or du is equal to alpha times lambda to the power of alpha dx. Okay, and when we integrate dv, which to find v, we end up with x plus alpha to the power of minus alpha divided by minus alpha. So that can be re-expressed as follows: 1 over minus alpha times x plus lambda to the power of alpha. Now it's a little bit piecemeal here, but it's actually fairly straightforward once you piece it all together. But it's just actually knowing precisely how to go about this to pick out the numerator and the denominator as your u term and your dv term. Okay, so anyway, let's proceed. So this is u times v, okay, and this is minus v du. Okay, so this is du over here, that's v here, that's u times v. Okay, u on top, v below, straightforward enough. Okay, well, the 1 over, that's the inverse of v there. That's the v, the 1, u is x times alpha times lambda over alpha, and the v term is 1 over the denominator there. Okay, that should simplify straightforward enough. Actually, all I'm doing there really is just tidying things up, so I won't really dwell on that too much. Okay, so that's just tidy up. So let's look at the two terms individually and evaluate them both as definite integrals. So I have I1 and I2 there. Okay, or this is the this is actually not I1. This is the result of I1. Actually, I shouldn't call it that. Okay. So essentially, that's slightly misleading because that's just not an integral. So just evaluate it there from infinity to d. Okay, because it's not actually an integral. So the first part there is x minus x over lambda to the power of alpha divided by x plus lambda to the power of alpha, evaluated from d to infinity. Okay, when we evaluate it at infinity, we get 0. When we evaluate it at d, we get minus dx, d times lambda to the power of alpha over d plus lambda to the power of alpha. Okay, so essentially the minuses cancel out, and that's what we're left at there, and that we get that expression there. And if you note earlier on that that is something we were expecting, d times the power d times the probability of x greater than d. Evaluating the second term for infinity and d, we work it out the same way, and that's where we get our expression there. So this is the key part here, is where we get the actual answer we're looking for, the expression we're looking for. Okay. So now it's actually just a matter of, this is the whole thing written out again. Those terms cancel out. We end up with just that. And when we evaluate it with the values we were given earlier, lambda, alpha, d, okay, what we end up with is the expected value of x minus d. That should work out to be, with a little bit of calculator work, 168.29. The overall answer is a conditional probability. So it is the expected value divided by it's a conditional expectation, so it's the expected value divided by the probability of that value, 0.75. That's the probability of being greater than d, greater than the first quartile. So 168.29 divided by 0.75, that gives us 224.39. Okay, so we'll leave it there. That's a lot of work done.